All right, algebraic expressions. I think I've said this before. I'll just say it again, just in case you're like, wow, I know this stuff already. Yes, I hope you do. There should be some review, especially the first couple sections. Part of the reason I'm trying to move a little bit quickly is I know you've seen this before, but that doesn't mean you remember it necessarily. And I know there's people in here who don't remember it, so I'm trying to go over it so we don't have these issues later. When I first taught this class, I didn't do this stuff, and I was like doing mini exponent reviews like in the middle of other stuff, and so I just decided to just do this up front. Anyway, that's my explanation. What's a polynomial? That's another word you've heard before, I'm sure. But what is it? What does it mean? So a polynomial in the variable x is an expression of this form. And so I know it looks a little bit confusing, but just know, let's read the rest of it. All the a's, a sub 0 through a sub n, are real numbers. So they're numbers like 1 or 2 or pi or something. So all the a's are numbers. X is the variable, right? We already said that the variable is x. And n is some non-negative integer. I think we mentioned this before, but what's an integer again? A whole number. So some non-negative whole number. So 1, 2, 3, 4, 5, 6, something like that. Okay. We say, as long as the first term isn't 0, we say this thing has degree n. So degree means the biggest power. You can see that the biggest power in this expression is going to be n. And so that we call that the degree. And then each individual piece, everything between the plus signs, we call a term. Okay? So, for example, a degree 4 polynomial would be any polynomial we could write down where the biggest power is 4. And so something like x to the 4th plus 3x minus 1 is a degree 4 polynomial because the biggest power is 4. But I just want to point out that the coefficients don't have to be integers. They don't have to be positive. They don't have to be integers. They can be weird. They could be like pi x to the 4th minus e. Right? Those are two strange constants, but they're still constants. And the biggest power is a whole number, and it's 4. And so that's what makes those polynomials of degree 4. Okay, the main thing you should be able to take away from this is when I refer to something as degree whatever, you should realize that means it's the highest power. And I will use the term term. That's kind of funny. I will use the term terms regularly, and you should just know what that means. It means one of the pieces of the function. So what's not a polynomial then? I remember when I first learned about polynomials, I remember thinking like, isn't everything a polynomial? And so what makes it not? Any thoughts about that? What would break this definition? Okay, yeah, good. So if it has a negative exponent, so you can see these are going to be non-examples. A non-example would be something with a negative exponent, like x to the minus 2 plus x, right? Even though this one has a positive, this one's negative, and so that's not a polynomial. So a negative would be good. What else? Or do you want a question? Yeah. Yeah, so generalize it. What is that? What are those going to do with the powers? Yeah, we just learned that. Fractional powers, right? So things like square root of x plus 4, right? Because that's x to the 1/2, and 1/2 is not an integer. Rational functions usually aren't, so things like y minus 2 divided by y plus 2 or something like that. If you think about dividing that out, you'll end up with a non-integer coefficient, exponent somewhere. Other functions like exponential, so like e to the x, which we'll talk about in a later section, that's not a polynomial. There's nothing about that's a polynomial, right? It has an exponent that's a variable. That's strange in itself. And I'll just say it doesn't necessarily have to be a square root. It could be any root, right? So like cube root of x squared, which is x to the 2/3. I hope we know that now. That's also not a polynomial, again, because it's not the power is not an integer. All right. Any questions about that? Are there questions about this definition at all? This is like I feel like it's a weird, scary-looking definition that doesn't have a whole lot of meaning to it. And so I don't want anyone to be like confused about something that's not a big deal. Okay. So let's remind ourselves how we combine like terms. I've already used that phrase before, like terms, and so I just want to remind you what that means. A like term are the terms that have the same variable raised to the same power, right? So for example, and I know you've heard this before and maybe it's not new, x squared plus 2x squared are like terms because they both have an x and both of the x's are raised to the same power. And so we're allowed to combine them in that situation because we have one of something plus two of that same thing. And so that gives us three of that thing, right? Great. And let's just practice real quick combining them, right? So we may have an expression like this, where we have some polynomial on the left, and it's being subtracted, or it's subtracting from it a different polynomial. The first thing we do in this equation is we would distribute the minus sign through and hit all those other those signs. So this negative is going to switch all the signs inside there. And so we'll have x cubed plus 2x minus 5, and then we switch all the signs. So we'll have a minus 4x cubed plus x squared plus 4x minus 10. And then we just look for common terms. Right? We look for terms that have the same variable and the same power. And so we would say, okay, there's two x cubes in there. So we can combine those two. And we can combine them into minus 3x cubed. We see that there are two x's. There's a 2x plus a 4x. And let's do the x squared first. I'm sorry. There's only one x squared. There's only this x squared, and so there's nothing to combine it with, so we just carry it over. And as I just mentioned, we have a 2x and a 4x. Those two can be added together to get 6. And then we have a 5 and a minus 10. And so the 5 and the minus 10 can be combined, the minus 5 and the minus 10, excuse me, to give us a minus 15. Right? You guys remember that? Yeah. Thank you. It should be 6x. Thank you very much. Does everyone see that? That should be a 6x. Otherwise, I would have more like terms I could combine. Yeah. Okay. Anyway, let's practice this in a distribution example. I didn't see the need to do any more of those. I just wanted to get a quick reminder. But we'll need that when we distribute, right? So when we multiply out algebraic expressions, we use the distributive property. And what that means, you probably know this as maybe FOIL, and it's called FOIL with just two terms. But when we have more than two terms, all we need to do is multiply each term in the first expression by each term in the second expression. So we take that 10 and we multiply it through and hit everything in the other one. And then we take the 4y and we multiply it through and hit everything in the second one as well. And then we combine like terms afterwards. So I'll do the 4y through. I'm going to take that 4y and multiply it through there, and we will get 24y cubed minus 28y squared minus 72. I'm sorry, I started looking at my answer. Jumping ahead of this. We get 24y squared. Sorry, don't write that down. Jumping ahead to my answer. We get 24y cubed plus 32y squared, 4 times 8, yep, and then plus 8y. So that's multiplying the first one through. And then we multiply the minus 10 through. Don't forget that this minus sign comes along with the 10, right? And so it's going to switch all the signs in the next one too. So we'll have a minus 60y squared we'll get a minus 80y and a minus 20. And then we just combine like terms. So let me pause for a second here. Let me write down combine like terms, see if there's any questions. It's okay, you guys remember that? No questions? So when we combine like terms, we end up with, let's see here, there's only one x cubed, and so we leave that one alone, 24y, y cubed, not x cubed. We look at the squareds, we've got a 32y squared minus 60y squared. That's going to be a minus 28y squared. There's an 8y minus 80y, so that's going to be minus 72y. And then there's only a single constant, minus 20, and so we just bring that down. And that would be good. Let's just get a quick practice with this, in case you haven't done it in a while. Give this one a try, please. So FOIL that one out and combine any like terms that you have. How many like terms are in this one? Just 2, right? Alright, well, let's take a look. So I'm going to multiply the 5y through first, and I'll get minus 15 yx plus 5y squared. And then I will multiply the 4x through and get plus 12x squared minus 4xy. So then when I, is that okay first? Oh, thank you. So when I'm looking at this, I need to have the same variables with the same powers. And so this one and this one are like terms because they both have an x and a y. Even though this one says yx and this one says xy, you can rearrange those by the commutative property of multiplication. And so those are the only two like terms. So you can't combine anything else in there because this has a y, this one doesn't, this one has an x, this one doesn't, etc. It needs to be the exact same, right? And so when we simplify that, then we combine those two and we get 12x squared minus 19xy or yx, either one, plus 5y squared. Questions about that one?
Does
Yes.
it matter if you put yx or xy?
Nope, either one's perfectly fine, yep. Right, you can multiply 2 times 3 and get 6, or you can multiply 3 times 2 and get 6. Either way is fine, yep.
Does it matter to put the 5y squared before the...
Nope, the order can be rearranged too. Yep, any of those would be good, and WebWork will accept any of them too. Yeah, just to be clear, like WebWork will accept usually, if it tells you to simplify a question, it's usually looking for something specific. But like you could enter 1/2 for 1/2, you could enter 0.5 for 1/2, you could enter 2 divided by 4 as 1/2, 10 divided by 20. Right? -2 divided by -4, so there's lots and lots of ways to enter 1/2, and it recognizes them all. And it'll do that with lots of different types of problems, so just be aware of that too. Other questions? I'd like to just briefly look at the next page. So let's take a look at that and just get it started. Yeah, I was wondering about that. Let's see what happened. I think it's doing it every half hour. So I wonder if it's going to be half-hour clips. That's okay. Can't wait to hear myself talk. It's going to be awesome. Have you ever done that, like recorded yourself and then you go back? Watching, it's even worse. But recording it, oh gosh. I'll just make sure it's there and then not listen to it. Okay. This is going to be a very quick review of factoring. And so what we're going to talk about on this page and the next page are 3 different ways of factoring. And specifically factoring polynomials. We're usually factoring polynomials. And so factoring is the opposite of multiplying, it's the opposite of multiplying algebraic expressions, right? So unlike the last page, we took something that was factored and we multiplied it out into this. Now what we're talking about doing is starting with something like this and going backwards and factoring it, right? So it's the opposite of what we just did. And we'll talk about these 3 methods. Looking for a common factor, trial and error, usually works with 3 terms, and then grouping terms. You usually do that with 4 or more. And so each will be discussed on the pages that follow. You can see below here is looking for a common factor, and then the next page is going to be the other 2, trial and error and grouping. And so I'll just say this again while I have a second. We only have 1 page left in the notes that I handed out, so if you haven't printed the notes, we will likely need them on Friday, so please do that by Friday. So looking for a common factor, if each term shares a common factor, you can basically divide each term in the expression by that common factor and put it out in front of the resulting expression. Right? Sometimes people call it like pulling something out, and I usually use that phrasing too. You can pull out something from this first expression, for example. So what does each one of those terms have in common in that first expression? 2, right? So the common factor in that first one is 2. And so we just go through, we write down the 2, and we're going to rewrite the expression after we divided each of those terms by 2. Right? So when we divide the first one by 2, we get 2x squared. When we divide the second one by 2, we just get x. And when we divide negative 8 by 2, we get a negative 4. Right? That's about as straightforward as a problem could be. If they're even, it's got to be a 2. It's got to be a 2, at least a 2 that this factors out. And I just wanted to take this 1 second just to note that these are the types of problems you can always just check. If you take something out and it doesn't look right, or maybe you try entering it into WebWork and it's not accepting it, something's wrong. And so you can always double check your answer by just multiplying out what you just tried to factor. Right? So you could start with your answer, FOIL, multiply that through, and make sure that you get back to the original. That's the original. Oh, it should be 8 though. Right now it's the original. Looks like it worked, and so we did it right. Right? But anyway, I'm not suggesting you try this every single time, but it's a good way to check your work if you're having a hard time entering a problem or something like that. What about the next one? What's a common factor in this one? So they all are divisible by 2. We've got an even for sure. I agree that x is a common factor because they all have an x, and x is the lowest power, x to the 1. What about y's, though? It looks like they all have a y, and they all have 2 y's. And so it looks to me like this factor is, the common factor is 2xy squared. Got a couple minutes here. Take 30 seconds and factor this one out. Right? So you want to divide everything in there by 2xy squared. There's a y to the third in the middle, but this one only has a squared. I'm sorry, was there... I don't know who asked that question back there. Does that make sense now? Okay. And does it make sense? I don't hear what you said. Okay. Right, so you just want to divide everything out. Another way to think about it is whatever you write inside the parentheses, when you multiply the 2xy squared back through, you need to get to the original, right? So you can think what do I need to write here so that when I multiply it by 2xy squared, I get 8x to the 4th y squared. And so the 2 is going to turn into an 8 when we multiply it by a 4. Right? The x to the 1 is going to turn into an x to the 4th when we multiply it by an x cubed. And then the y squared is going to turn into a y squared when we multiply by 1. And so we don't have to add anything else in that one. Right? So I'm just going to pause for 30 seconds, and we will resume, and we'll finish this up as soon as you've checked with someone next to you that it looks good. All right, so maybe we can get out of here a couple minutes early, but check with someone next to you, please. If it's not quite right, get some help, correct them, they can correct you. Alright, so when you factor this, and the second one you'll get a 3x squared y to the first. When you multiply that through, you'll get your 6x cubed y cubed. And then the last term is just going to be a minus y squared. Because again, when you multiply that back through, you'll get back to the original. Any questions? Alright, have a great day. Please remember that there is homework due this evening. I'll be checking email, but I go to sleep a lot earlier than you do, so you should, if you're going to email me, do it sooner than later. Have a good one. So last time we were talking about factoring, and if I can find that other page, I don't have that other page with me right now. But we had talked about already just pulling out a common factor. That's where we left off last time, was just simple common factors, right? And today what we're going to talk about are two other methods, which is factoring a trinomial. We'll talk about two different forms of that. And then we'll talk about grouping terms as well. And so a trinomial is a polynomial that has three terms, right? So tri means three, and so they all look like this. They all have this form. ax squared plus bx plus c. And a, b, and c in this equation are just numbers. They're real numbers. And we call this method the trial and error method because it involves thinking of factors, seeing if they work, and if not, trying something else, right? So trial and error. Or sometimes, I think people call this guess and check, maybe. Okay, so to factor these kind of polynomials, we usually have to think of a factor of the last number c, and I'll call those factors r and s, such that you add those numbers together to get the middle number b, right? And you multiply those numbers together to get the last number c. And so we want to think of factors of c that add up to b, right? So factors of the last number that add up to the middle number. And so I'm sure you're all familiar with this, but just a little reminder here. On this first one, we want to think of factors of -6 that add up to 1. And so first of all, since it's negative, one's got to be positive and one's got to be negative, so that when we multiply them together, we get a negative. And what are the two numbers that do that? So 3 and 2 certainly multiply together, but one of them's got to be positive, one's negative. Which is the positive one? 3 is the positive one, and we want, so let me write that down first. So one of the factors is 3, the other factor is -2. And we like those factors because notice, when we multiply them together, we get -6. And when we add them together, we get +1. Right? And so that means that we can factor this trinomial using this form, x plus r times x plus s. And so our final answer might be, that x squared plus x minus 6 equals x plus 3 times x minus 2. And as we talked about last time, you can always check these, right? You can always check a factor problem if you want, just by distributing it out and simplifying, and you should get back to the original, right? So you can always double check those kind of answers. Is there questions about that? I know you've done this before, but does anyone need like a reminder about something related to this at all? Okay. I'm going to leave this other one for just a moment and let you try it in a second. But let's look at the other one first. So what's the difference between this bottom one, like what makes this bottom one more challenging than this first one?
The coefficient of the x squared.
Yeah, the 6 in front of the x squared, right? So in this first one, our leading coefficient was a. I'm sorry, it was a equals 1. And in the second one, a is not 1. It's 6. And that makes it more challenging, right? And so not only do we need to think of factors of the last term 5, but we also need to think of factors of the first term of 6. And don't get too caught up in these formulas, but basically what ends up happening is we're going to factor it into this form right here. It's going to look something like this, where there's no longer a there's no longer a coefficient of 1 in front of the x. And when we multiply all that out, what we need are these things to be true. And so don't get too caught up on this. I just know some people like to see formulas sometimes. But we need the factors of A, P, and Q. And we need factors of C, that I'm calling R and S. And we need P times S plus Q times R to equal the middle number. And so it just gets a little more complicated. I wouldn't recommend sort of spending too much time in those equations and wallowing around in it. Usually I just kind of jump right to the answer and just start working it out. And then if it doesn't work, I erase it and try again. But just in case you want a different approach, and I want to illustrate how it doesn't work sometimes, I'm going to do this one wrong first before we do it right. So you're welcome to write this down. You don't have to necessarily because it's going to be wrong, but I just want to sort of point out that why it's called trial and error, just in case you run into some problems and you need to try them more than once. And I hope you do, because that means it's a good problem. And so I might think, okay, let me think of factors of -5. I'm thinking of factors of -5. There's only 2 factors of -5, 5 and 1. And one of them's got to be negative, right? And so maybe I'll choose S. I'll choose 5 for S. It looks like I wrote S twice. I'll let my S be 5, and maybe I'll let my R be -1. And so those, you can see, are my factors of the last coefficient, the last term, I mean. And what we need is we need 2 more numbers so that when I multiply PS and QR, I get the middle term, which is 7. And so now I need to think of factors of 6 that I can use. And so there's more than one factor of 6 that's possible, right? Because 6 has 6 and 1. It could also be 3 and 2. And so we just need to choose which one to try. And I'm going to try again. I'm going to try the wrong one. So let's try, maybe you think, okay, 6 and 1 are a good choice. Let's see if that worked, right? And so we can kind of see if it fits into this form. We need P times S plus Q times R to be 7, because when we multiply out that factored form, it needs to add up to 7. But in this situation, PS plus QR is going to be 6 times -1 plus 5 times 1, which is -1. We're going to get minus 6 plus 5. We needed it to be 7, and it was only -1, right? We wanted it to be 7. And so this didn't work. I just want to point out why sometimes why it's called trial and error. And so usually that means, okay, these aren't good factors. These were the only ones that we had an option with, 6 and 1. So let's try 3 and 2 instead, right? And just want to be real clear about sometimes you need to try it more than once. And so let's try instead R equals 5, S equals -1. And then let's use 3 and 2 instead. So Q equals 2 and P equals 3. And if we do that way, notice that they actually add up to the correct thing. If we do P times S plus Q times R, we do get 7, right? Because we'll get P times S would be -3 plus 10 would give us 7. So that's good. Check. Oops. Holler at me if I'm off the screen next time. That's good. And so those are the factors we want to use. And so then we can write down our final factored form. as x plus 2. I'm sorry. Got ahead of myself. As 2x minus 1 times 3x plus 5. And this is my Q, there's my S, there's my P, and there's my R. So let me just let you write that down and let you catch up before I sort of just say one more thing about that. And let me see if there's any questions too about that at this point.
Yeah, so, I don't know, does it matter, so because if it's two factors of, so 2 times 2 equals A, is the order important? Is there a certain way that, is it just kind of a trial and error, so you would get the 2 and then whichever one's multiplied properly?
Yeah, and so I think your question is, like, how did I know to put the 2 with this 1, the minus 1, and the 3 with the 5,
Yeah,
like
so
that kind of thing,
the
right?
specific P with S and Q with R, it's just kind of you swap them and then the one that works is the correct one.
Yeah, you have to, that's another part of the trial and error, yeah. So I knew that I wanted like a positive 7, and so that means I needed a big positive number, and then I was going to subtract something from it to keep it, make a 7. So that's why I like the 2 and the 5 on opposite sides, because I see that they're going to multiply together and give me 10, and then I'll end up subtracting 3 from that, which will give me that 7. So yeah, there's a little trial and error part of that too. Yeah, thank you for that. And so I was just going to mention that, you know, again, I write down this formula because it's like in the book, and that's how they write it down. When you're doing these in practice, I just know, let me just do this real quick. I just start doing this. I know it's going to look like that. I know there's going to be an x here and an x here. And then I just start filling in factors a little bit until something makes sense to me. And I don't just like guess. I'm not just like, well, maybe it's this and maybe it's this. I'm kind of thinking about what it's like, but I just sort of jump right to this and do a couple trial and errors until I get the right one. That's my personal approach to it. I don't recommend you necessarily try to use these formulas, but the formulas are true because when you multiply out the factored form, those need to be true, but don't let them confuse you. And I remember thinking back to like the first time I learned factoring, you know, I don't remember when you learned it, maybe in middle school the first time or whenever you learned it the first time. I remember thinking like it was so confusing because I didn't know how I would ever come up with these numbers in that order, right? And then I remember after you do a bunch, they kind of almost, dare I say, you get to the point where they're fun almost, where it's kind of like a little puzzle, and you get some intuition about what numbers to pick and where to put them. Right? Just so practice makes perfect, really, in this case. The more of these you try, the less confusing they become, and the more sort of intuition you build about them. Questions about that? Okay. Let's look at grouping terms. I'm going to do maybe one of these and then ask you to finish the other one. So, yeah.
What about, I recall like there's another method that you can like multiply the coefficient to the C value, and you can also
You can multiply which coefficient?
multiply the coefficient 6 to -5, and then do it from there.
So you get 30, and then I'm not familiar with this method. I'm trying to maybe figure out what that is.
Yeah.
And then what would you do then?
And when you get the answer, you then multiply the real numbers with, not multiply, I mean divide by 6 again.
But if you multiply by 5, 6 times 5 to get 30, and then you divide by 6, you get back to 5.
No, I mean when you get like the factors, you will divide the real numbers and the factors by 6 again, and simplify the fraction, and the denominator would become like the coefficient for the x again.
Okay. I'm not familiar with that, but that's, if you want to do it that way, that's totally fine. And maybe I should also said this at the beginning, like, people learn this different ways for sure. And if you feel comfortable doing some other way like that,
No, because I also like don't feel sure about this because I don't get the same answer. That's why I was asking maybe.
okay, I'm not familiar with that method. I'm happy to look at it afterwards, and maybe we can figure out what it should be. Is anyone familiar with that kind of, you know what he's talking about?
You do 6 times -5.
Yep.
Which gives you 30, and then -30, and then you would do the factors of that, which would be like -3 and 10. And then you do a over each factor. So 6 over -3, or yeah, 6 over -3, and then you reduce it, and then you do 6 over 10.
Mm-hmm.
So you get.
So you get
3x
1
plus 5, and -2 minus 1.
Okay. I mean, that sounds really great. I'm not going to write it down. I hope you don't mind, but that sounds very legitimate way to do it. Yeah. So maybe I should just write it down. I don't know, in case anyone's really interested in that. So it was 6x squared plus 7x minus 5. I've never heard of this method before, but it sounds like it could be good. And so you do 6 times -5. So this is our a value and our c value, and you get -30. And this has factors 10 and -3. But what about -10 and +3?
That still works.
So you have to write all of them down?
No, well, I don't really think it
We
matters.
just like write whatever like -30 is, basically.
But it's also 6 and 5.
You like get times it, you're gonna multiply 6 times -5, so -30,
Mm-hmm.
and then you find the factor -30, so -3 times.
Oh, that equals 7, sorry.
Oh, that add up to the middle number. Now I gotcha.
Yeah.
Okay, that makes more sense. And so this is good because 10 plus -3 equals 7, and that's the middle number. Okay. And so then you do 10 over 6, which is, and you reduce that, I'm assuming, which is 5/3.
Yep.
And the other one too?
6 over -3.
Oh, well, -3 is on top though, right?
No, it's a over each factor.
Oh, it's a over.
Yeah.
So this one should be switched. I don't know if this is helpful or just confusing everyone. But it sounds like it could be really good. I've never heard of this before. So you do a over the factor. So 6 over 10, which is going to be 3/5. And then you do 6 over -3, which will be -2. Okay. And then how does this help us?
Then you do -2x minus 1. I guess it's technically -2 over 1.
Okay, yeah, -2 over 1.
And then, so it would be -2x minus 1, and then.
Oh wow, this is really interesting. So this is like, this becomes -2x. Well, let's make it positive 2x. Usually make that one positive, right? And then this one becomes -1.
Yeah.
And then this is the 3x. And this is the 5. That's very interesting. I've never seen that before. And so then you get your final answer of 2x minus 1 from those two, and 3x plus 5 from those two. So you are really using those formulas on the previous page. You're just doing it in a very interesting way. I'm sorry, can you say that again? Yeah, let me rewrite that because it's that's 6. It's 6 over -3, and let's just keep the negative with the bottom. Is that better? I don't know why this is so blurry.
Where did you get the 6 over -3?
It's a divided by these two factors, so it's a divided by 10 and a divided by 3. This is very messy. Why don't you let me write this up in a better way and present it later? Yeah. Oh, and then you group.
Yeah.
That's a good way to do it too. Cool. Anyway, maybe I'll try to write this up in a more easily understand. This makes sense to me right now, but I'm sure it doesn't make sense to other people. So, but quite frankly, and I appreciate all the input, I really do. But I'll just say again, you're welcome to do it whatever makes sense to you. Let me see if I can figure out why this is so blurry. It's pretty blurry, right? I think. Okay. Cool. So it sounds like most, or at least some people, have their handle on this already. So that's good. Yeah.
That's the way I do it, so that's fine. And like,
Yeah. No. Yeah. Any way that you get the right answer is a great way, provided you didn't look at someone else's papers. All right. The next. Is there any other comments or questions? I really hope I didn't confuse anyone. If anything, you just got 2 or 3 ways to do it. And I'll do my best to write up a nice write-up of what that other method was. Okay, grouping terms. This is a method you want to use when you have 4 or more terms, and it kind of sounds like it's what you end up doing in some sense with the trinomials. But anyway, when you have 4 or more terms, which usually means that you have something bigger than an x squared, like an x cubed in this one, right? It helps to group the terms with a common factor, and then factor each grouping. And what happens when you factor the individual groupings is another final common factor sort of pops out. So for example, when I look at this first one, I see those 2 have a common factor, and I see that those 2 have a common factor. And so I'm going to make this my first group, and this will be my second group. And I'm going to factor out something common from each one. And so what's common in the first one? There's an x squared in both those first ones, right? There's an x squared in the first term and in the second term. And what's common in the second one? 4. And so in the second one, we can factor out a 4. And so we get 2 groupings of factors. And so we'll get x squared times x plus 1, plus 4 times x plus 1. And so we just pulled out a common factor from each one. And the interesting thing with this method is usually that you end up with another common factor, right? So now each of those terms has a x plus 1 as well. And so now we can factor out the x plus 1 and get a final form that's very nice and factored. And so this could be x plus 1, and we're left with x squared plus 4. Right? And so the x squared came from right here, and the 4 came from right there. Oh, thank you. And so the nice thing was, again, like once we grouped them and pulled something out of each one, they each also have an x plus 1, and we're able to take that entire thing out front, and what's left from this piece is an x squared, and what's left from this piece is the 4. Questions about that at all? Okay, I'd like you to finish the last 2 on this page. So this one here, you're going to want to group those 2 and those 2 and do the same thing. And then there's also this one at the top that we skipped over that I'd like you to just give a try as well. So take a few minutes and try that. Please, when you get an answer or you're stuck, please consult with someone near you, or someone's. More than one person's fine. And if you need some help, by all means, let me know.
So I wasn't sure whether just because I made a mistake here, like I made a mistake simplifying this, but now I'm sure of the method now.
Oh, and then you multiply through letters on that.
Yeah, so what you do is just you just get rid of the coefficient and just do it as if this is the polynomial, the trinomial you're trying to factor.
Yeah.
And then you just put 6.
And then you divide it
by 6, and the denominator you move the facts.
I really like that maybe. I like that way a lot better than the other way. I'm going to maybe write that down quick.
I wasn't like fully convinced that this would work because I made a mistake in there.
What is the last number?
It's
It's 6x squared plus 7x minus something. 10? 5?
yeah, 5.
Did you do this?
Sorry.
Oh, I'm still in my top one. Oh, okay. Every time I see a 5, there's a 35.
So you multiply that into there, I see.
I just got
So you just change it.
part. This part.
Oh.
It's not explaining everything. X squared. Yep. That's right. And then you're left over x squared, x plus 2 minus 6, x minus 6.
Yeah,
Like this. But then that's the hard part, when you factor out. So just do that and then we'll compare answers. Because I don't know what you probably do. Probably better than that. I'm going to put a biology. I'm pro on biology. Anything that has to do with science.
At this point, you have the same factor that you're.
Yeah, but anyway, I don't know why I got X plus 2.
You have your own Oh, where you kind of set up all the factors.
That's what I meant. How did I get that?
You probably forgot to take the negative out of the because you're dividing negatives.
Actually, okay. So then, what did that give me? 60 divided by 6. That's okay. So factoring is like divided by 6.
You're in basic math.
That makes sense. So it would just be, it's a little funny, I got the right.
I really like that.
I just got that
Like,
stuff.
I'm gonna
So it was
share that
x
as
plus 2, x squared minus 6. Okay.
So everyone had a chance to check with someone? I feel like we should move on anyway because we're running short on time here. Remember, today's a short day. And so in this first one, what are the factors that we want to use? This top one that we missed. We want factors of negative 35 that add up to negative 2. Very good. All right, so we have our R is negative 7 and our S is positive 5. And notice that when we multiply them, we get negative 35. That's good. And when we add them, we get negative 2. And that's also good because that's what we want. And so we can just say that x squared minus 2x minus 35 can be factored into x minus 7, x plus 5. Nope. Yeah, that's fine too. And you could also write, we could change the order of those too, right? You could write x plus 5 times x minus 7. That's also good. Is that one all right? Okay. What about this other one? So we've got two groupings here. I'm going to pull an x squared out of the first one, and we'll be left with an x plus 2. And then I'm going to pull out a negative 6 out of the second one, and we'll also be left with an x plus 2. Actually, this is usually where I like to sort of mess it up at first. Did anyone do this? Did anyone make this factor out a positive 6, and then you end up with minus x minus 2? You could do that. That's true, right? So this has a common factor of 6. That's true. And if I factor a 6 out, I'm left with a minus x minus 2. Does that make sense? Because when I multiply that back through, I'm sorry, minus x. Yeah, minus 2. When I multiplied this back through, I would get that. But why do we not want to do that in this particular instance? Yeah, you want these two things to match so you can factor something else out. And they don't match when you do that. And so if when you're looking at this and you're like, that doesn't really match up. It does match if instead of factoring out a positive 6, we do what I did originally, which is factor out the negative 6. And so that makes it, when we pull out a negative 6, we'll have a positive x plus 2, and now those are the same. Right, so just in case I think that your intuition usually is when you see those two, that 6 is the common factor, but you want to be careful and make sure that you pull out a negative 6. Does that make sense? Because now they have a common factor, and you can remove that common factor x plus 2 as well. You get something like that.